Yep.
How do I look?
You look great.
Okay. Let's get started. All right. Number, what's this, 7 or 8? Laws of thermodynamics. Dynamics. Did I spell that right?
Yes.
How many laws of thermodynamics?
3.
3, but physicists are so disorganized. They came up with 3 laws and then they figured out what?
They forgot one.
They forgot one, and instead of doing 1, 2, 3, 4, they called it 0, 1, 2, 3, 4. So the 0th law of thermodynamics, I don't even know why they spent any time doing it.
A equals B.
If the heat content between A and B is the same, and the heat content between B and C is the same, not even the next 3. And the first law of thermodynamics, a lot of algebra. E weights.
Negative Q.
U equals.
Negative Q minus W.
U equals.
Negative Q minus W.
Q minus W. What is that telling us? The internal energy of an object
Equals
the heat content of that object minus the work. And let's get some more detail. Delta U equals, Q can be what? MC delta T, or it could be 0. Or it could be 0, yes. But algebraically, it could be MHF, MHV. Make sense? Minus work becomes P delta V. And that negative is important there. Because when volume expands, are we doing energy on the system or on the environment around it? Environment around it. When the volume decreases, are we adding internal energy to the system or decreasing it? We're adding when the volume decreases, we're adding energy to the system. So that negative is very important. Be able to explain that. So this is the equation we're real concerned about. We talked about 3 different systems, and we didn't talk about a 4th. And those of you heading for a 5 in May want to look at that 4th. What are the 3 we did talk about? Adiabatic.
Isobaric.
Isovolumetric.
Adiabatic. Isobaric.
And isovolumeric.
And I'm sure I'm spelling this.
There you go.
Volumeric. This equation here is which of those 3? Isobaric. Agreed? Adiabatic, what does this become?
Negative W.
Negative W?
Nope.
Adiabatic. What are we holding constant for adiabatic?
Pressure.
Pressure's always constant.
Temperature.
Temperature we're holding constant, so therefore what drops out? MC delta T. So for adiabatic, the internal energy of a system becomes
Negative.
the work. The work. Agreed? And isovolumeric, what drops out? P delta V, and it becomes internal energy equals. Okay, we'll continue tomorrow. A lot of you want to change the pressure. Are we changing the pressure in this law at all?
No.
It's really the only thing that doesn't change. Everything else is delta, but pressure stays constant. The system is right here. It's got atmospheric pressure. Agreed?
Right.
Or it's in an enclosed tank, and in which case, what does it got? What does it have?
Gauge pressure?
It has gauge pressure. Is that what you said?
Yeah.
I'm sorry. It has gauge pressure, okay? It's not like we have... So this first law is the complicated one. And this is what you'll see on the May test. So this looks like what? Adiabatic, isobaric, or isovolumeric? Isobaric. Pressure stays constant. I meant to put this. Right? Isovolumeric, what drops out? What drops out? Isovolumeric.
Delta V.
P delta V, because the volume stays constant. There's no delta V, therefore, right? So the entire internal energy is caused by MC delta T. And I keep saying MC delta T, but Q can also be represented by what? MHF or MHV. Although there's no T in MHF or MHV, we are adding heat, aren't we? Because that's the only way you're going to go from a solid to a liquid is by adding heat, increasing temp. All right? Now, a question. Fill in the blanks. Matter does not contain blank, it contains blank. Matter does not contain
Energy.
Temperature.
heat. It has
Energy.
internal energy. Heat is what?
It's a measure of
The temp is a measure. Heat is,
Movement of it.
it's movement. It's movement. It's movement from where to where?
Hot to cold.
Hot to cold. So heat is a dynamic thing that's moving from one area to another, from high internal energy, if you will, to low internal energy. So metaphorically, if we were looking at electricity and magnetism, what's equivalent to heat? Voltage, current, or resistance?
for what?
Current, because current is the movement from high voltage to low voltage. Heat is the movement of high temp to low temp, or high internal energy to low internal. What's the second law? AKA law of
Entropy.
entropy. All right, I drop a deck of cards. Does it stay nice and organized when it hits the deck? It scatters, it increases chaos. I hermetically seal this room. What does it look like a million years from now?
Garbage.
Looks like a dump. I don't care. If you control the humidity, control the temperature, could you do everything in here, it's going to look a heck of a lot more chaotic than it does right now. Things are going to fall, things are going to destroy, they're going to smash. Right? It's certainly not going to look as organized, if you want to call this organized. It's certainly not going to look as organized as it does today. So entropy, increase of what? How does that explain the fact that heat moves from hot to cold? Because cold is very organized. It's usually a solid. It certainly has less motion. So it's more organized. Does nature law? We didn't spend a lot of time on this third law. What's the third law?
Mechanical energy goes.
Yeah.
100%.
When in doubt, look at something like this, and what comes out of here? If I'm changing from hot to cold, I got to be kicking out what?
100%.
Mechanical energy.
So you can't do cold to mechanical. You can't do hot to mechanical energy.
Does this make sense? Can I take this cold out?
No.
It makes no sense at all. There is no machine that could go from hot to mechanical energy 1-to-1 at 100% rate. Okay, if you can do it, you're the next billionaire, but it can't be done. Cars have exhausts. Air conditioners have an output. Okay? There's got to be a colder reservoir for this thing to dump into. And by the way, some of it kicks out and we can create mechanical energy. But there's got to be a cold reservoir. And the Carnot cycle, we spent no time on. TH minus TC over TH. Okay? We got to have a cold reservoir. If we did not, TH over TH is 1. That implies 100% efficient. Carnot says that's not possible. We have to have some value for cold air. We have to have.
Like Formula One cars, what they do is, you know that energy wasted? They have like this thing called like the kinetic energy recovery system, where like energy wasted by brakes and stuff can kind of be like put back towards the car.
Really?
Yeah.
Interesting.
Yeah, for like a short period of time.
Like, makes more power.
Yeah, for like an 80 horsepower boost for a couple of seconds.
Very interesting. Yeah, you know, the big push now is to be able, you know, you see recycle wasted stuff that's coming out and put it back in and get it to work for you. That's a good example right there. I mean, this idea of just pumping out, you know, we call it a cold reservoir, but you put your hand on the exhaust of your car, there's some heat there. It's just a lot colder than the heat of the internal combustion engine.
Yeah.
So therefore, but that heat in that exhaust, if there was some way we can capture that heat, and it sounds like they're doing some of that with what you just said, and recycle it, or make the exhaust colder, then we're getting more mechanical energy.
Yeah.
Does that make sense? If we make this colder, we're getting more mechanical energy out there.
there is ways to recycle exhaust, but it doesn't do it all the way.
I got to think the expense of that is prohibitive.
I mean, yeah, it's only on Formula One.
Yeah.
That's, yeah.
The expense would be